We acknowledge the first Australians as the traditional custodians of the continent, whose culture is the oldest living culture in human history. We pay our respects to elders, past, present and emerging, and we respect their cultural heritage, beliefs and relationship with the land. We extend our respect to all Aboriginal and Torres Strait Islander people here today. They share the memories, traditions and hopes of the traditional ancestors with the new generations today and in the future. We would also like to thank them for looking after this land for thousands of years.
Good afternoon, everyone, and welcome to day 4 of SciFest 2022. It's been an incredible week for those of you that have joined us for multiple sessions so far. All of these programs have been able to be put on due to funding from Inspiring Australia New South Wales. So we're really grateful that we've been able to run these amazing science sessions all for free. We will be sharing the recording of the session as well if any of your students in your class might have missed it or you want to watch some of the incredible experiments again. We will be having some questions coming through to the Q&A as well. So if you've got questions for us, put them in the Q&A, but there might be some times that our scientists ask you some questions and you can respond to them in the chat. So I'm going to hand over now to the team from Street Science for the fabulous Breaking Point session today. We've got Steve.
Thanks, Karen. How are we going, guys? We pretty good? Excellent. Now, let me get this balloon out of the way. A very good afternoon to you. My name's Steve Liddell. I'm a science communicator. I also run a business up here in Brisbane called Street Science. We've been around for just over 10 years teaching science to kids all over the country. So it is an absolute pleasure that you guys have come along today to join us for a virtual incursion, which is really, really cool because it's not just any old incursion today. We are celebrating National Science Week. And as a science communicator, it doesn't get much better than the middle of August every single year. The theme for National Science Week this year was glass more than meets the eye. So we're going to be doing some demonstrations today that involve glass. In fact, we'll be looking at how glass is made. We'll be looking at the properties of it, how we can cool it and shape it. We'll be cutting some glass a little bit later on. We'll be looking at different types of glass and how they can withstand cool temperatures and hot temperatures. I'll be grabbing some liquid nitrogen out, doing a few liquid nitrogen demos because everywhere I go, people say, "Science, Steve, why didn't you bring the liquid nitrogen?" So today, I've brought some along for you guys as well. Heaps of other crazy stuff. And I'll be joined by a very special guest. I'm not doing the whole show today. I've actually got an amazing science communicator who's going to be joining me. I'll introduce her a little bit later. Now, I believe that the chat room is open, and I might just see if I can get it up on my screen as well so I can see when you guys are typing away. There we go. If you want to drop any questions in, you're more than welcome to type them in. I'll just keep an eye on the side of my screen. Let me throw a question out there to you guys. In fact, if you know the answer, drop it in there. We're talking about glass. Today's show is called Breaking Point, the way it shatters matters. Who was the first civilization to work with glass? Do you know? If you're in a classroom, teachers, throw that question out there. Who was the first civilization? Was it the cavemen? Was it the Egyptians? Was it the Greeks? Does anyone know? For context, it was about 5,000 years ago. So a long, long time ago. I wasn't even born back then, 5,000 years ago. Some answers coming in, 5H, good on you, thinking it's the Greeks. I said cavemen, Egyptians or Greeks. There's your 3 options. I'll give you 5 seconds or so to drop your answers in there. Here's a little hint. They were actually producing, they were working with metals, and obviously metals have to get really hot, and they had sand in the environment. The sand got really hot. They accidentally produced a little bit of glass. They then did some experimenting and they started producing glass beads for a decorative purpose. So let me have a look. Bam, 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 bam. You know what? You guys are pretty clever. It was the Egyptians. Yeah. Maybe some of you guys quickly Googled it. Is that right? All right. Before I get the liquid nitrogen out, before we light things on fire, let's talk about glass. First of all, do you know how glass is made? Because I've got some glass right here. I've got an hourglass, some nice transparent glass at the top and the bottom. Sitting in the top is some coloured sand. To make glass, we simply need to grab some sand, some silica or silica dioxide, and we heat it up. Lots of sand into a kiln or a really, really hot oven. We get it up above 1700 degrees Celsius. Then it starts to melt. It turns into an orange liquid. If we want to colour our glass, at this point, we can go and add some oxides or other additives, mix it all through. It goes from its beautiful, solid, crystalline structure. Once it heats up and turns into a liquid, it starts to change. As we cool it down slowly. As we cool it down, we mould it. The way we cool it down is really clever because it changes from our crystalline molecular structures to a really haphazard, a little bit of a irregular structure. And we say it's amorphous. And we get this beautiful, transparent or translucent sometimes, beautiful glass product. So that's how we make glass. We're going to be working with lots of glass today. Now, let me get him out of the way. When you think of glass, what do you think of? Is it the beautiful glass windows in your classrooms? Is it the glass utensils in the kitchen? Or is it the glass in your granddad's spectacles? That's what I think of. Now, glass in spectacles like this has been shaped in a special way. We've shaped it into a lens. And the way they work, I've got big spotlights in my studio today. Light is coming down, smacking into me and different objects and bouncing around the place. If we are short-sighted or long-sighted, we can place these lenses in front of our eyes, and when light bounces off an object, it hits the glass and it changes direction. It changes the focal point so that it focuses on the retina in our eye, which is where it needs to be. And therefore, we can see more clearly. Let me show you a big version of a lens. Here we go. Now, I've got my spotlights. The light is bouncing off me. It's reflecting and heading towards a camera right in front of me. That then sends a signal to you somewhere in Australia. If I stick a lens between me and you, we should be able to change the way that light travels. It changes direction slightly as it passes through this lens. So we should, let's have a look and see. We should be able to see a distorted picture. All of a sudden, those waves of light travel to you through a different substance. They change direction just ever so slightly, and you guys hopefully see my face looking a little bit different. All right. Now, I'm going to get this balloon out of the way. Guys, because my mate Taz, she wants to come in here and teach you guys a little bit about glass optics. So this balloon cannot be in the way. So I'm going to get rid of it. But it's National Science Week. So I can't just go and pop my balloon. We need to do something special. How about we set it on fire? Now this balloon, our special street science balloon, is filled with a special gas. I wonder if you guys know what's in it. In the chat room, if you think you know the name of the gas inside this balloon, have a look. It's floating around. Drop the answer into the chat room. Teachers, if you've got a whole class of students, put the question out there. Science Steve has a balloon. The gas inside of it is less dense than the air around us. What is the name of this gas? I'm going to give you a moment and I'm going to grab a flamethrower. Oh, there are lots of answers coming in. Bang, 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 bang. And it's all the same answer. This is so cool. You guys are amazing. Let me grab my flammable substances. Let me grab my flamethrower to help get it out of the way. Okay. I'll give you 3 more seconds to get your answer in. 2 more seconds. 1 more second, and I'm going to close that down. Okay. Turramurra Public School. You guys have the same answer as just about every single person in the chat room today. Now, I think we have something like 3,000 people in this broadcast, scattered all over Australia. And everyone said the exact same answer. So, students, if you're in the classroom, on the count of 3, I need you to shout out the name of this gas. You ready? Because you guys are amazing. Name of the gas. 1, 2, 3. Did you guys say helium? If you said helium, well done. You are not correct though, okay? Everyone thinks it's helium, but it's not. When I go to birthday parties, hang out with kids on the weekends, build rockets and shoot them around, there's often balloons that float like this, and they are normally full of helium. But no, no, no. We're in the street science studio. This balloon is not full of helium. I want to light it on fire and make a big fireball for you guys because we're celebrating National Science Week. It's not nitrogen either. So for my mates there, I can't see whereabouts you guys are, but you're shouting at me. I said nitrogen. You're wrong as well. I'm sorry. It's not nitrogen gas. This, my friends, is hydrogen gas. It has an atomic number of 1. It loves to react with oxygen. When it reacts with oxygen in the environment around us, it makes H2O. I'm going to create a fireball that makes water. If this was full of helium and I got a lighter and some fire and I brought it nearby, it would pop the balloon. It would probably make my special guest jump and squeal, but it wouldn't make a fireball. Helium is inert. It does not catch on fire. Hydrogen, massive fireballs. So, I don't want to get too close to it. Let me get rid of my silly glasses and put on my safety glasses. I'm going to grab my flamethrower and I'm going to back away into the corner. I'm going to light a little flame. I'm going to bring it closer. It's going to go bang. It's going to make a big fireball that lights up this room. You guys are going to give me a massive round of applause wherever you are, and then I'll invite my mate to come and join us. All right, are we ready? I hope so. Okay, I'm locked in. Let me get my lighter ready in case I need it. Let's get a little flame. Oh, perfect. Are we ready? I'm going to get rid of it. This might be loud, okay? Anyone in the studio near me? Cover your hands over your ears. Here we go. Ready? 3, 2, 1. Oh! Golly gosh, make some noise. Oh, I'm glad that's done. Let me get rid of my flamethrower and welcome in a very special guest to the studio. Come on in, the wonderful Tasman. How are you, Taz?
I'm doing fantastic. How are you, Steve?
I'm pretty good. I'm excited.
Yeah.
Because it's day 4 of National Science Week. How many shows have we done this week?
Oh, I've lost count. So many.
We have worked with thousands and thousands of students, including you guys. So, Taz, I'm going to get out of the way because you've got something pretty crazy going on there. I'm going to shuffle and I'm going to leave you to it. Enjoy.
All right. So what a start to the show. What a bang. I felt it all the way over in the corner of the studio. That was crazy. Now, with me today, I've brought a few materials to explain a little bit more about refraction. Steve touched on that just a little bit already, but I'm going to go a little bit more in depth. So I've got some materials here in front of me. Let's observe. With me here, I have a large beaker. Inside of that large beaker, we can see that I've got what looks like water. Now, the water, the light from my studio lights here can travel straight through it. That's why we can see through water. But I do have something else in there as well. I've got a ping pong ball. Now, my ping pong ball, light can't travel through it, right? The light hits the ping pong ball, it reflects and it goes straight to the camera there so you guys can see it. Now I'm going to reach in there and grab out my ping pong ball. Oh, there seems to be something else in this beaker here. It feels a little bit strange. I'm going to see what I can get for you. Oh my goodness. I think you guys might have seen these before. These are Orbeez. Look at these Orbeez. Look at them go. Now, Orbeez are very slippery. They're also 99% water, right? So the other 1%, that's a material called sodium polyacrylamide. Very big words, right? Now, the 99% water, that means the Orbeez have a very similar refractive index as water. So that is why when the Orbeez are in the water, we can't see them. But when we take them out, we absolutely can. So once again, that was a very similar refractive index between the Orbeez and the water. But we're not here to talk about Orbeez today. We are here to talk about glass, right? So glass has a very similar refractive index to this liquid that I've got right here. Looks a little bit like maybe apple juice, maybe cider. No, it's oil, regular old cooking oil. Now, cooking oil has a very similar refractive index to glass. So if I take my glove here, I don't want to get an oily hand. That would be a little bit gross. Get my glove on there. Beautiful. And I grab my glass beaker and I'm going to put it into the oil. Now, at first, we're still going to see the glass. Can you still see it? Yeah, you can still see it. That's because there's air inside the beaker. So we can't actually see the glass. We can see the air. But if I push it down a little bit further, whoa, did that glass just disappear? Sure looks like it, doesn't it? We can still see the writing on the side of the beaker there, but the glass, we can't see it at all. That's because the glass has a very similar refractive index to the oil. So I'm going to grab my beaker back out. Let's have a look. Hang on a second. It kind of looks like I changed the shape of the beaker, doesn't it? But that can't be possible. I think this flask may have already been sitting there in that oil and we couldn't even see it. So we'll pour the oil back out and we'll try it one more time. We'll have a little look. So flask going in and we can still see it because of the air in the flask, but then glug, 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 filling back up and it's disappeared. Is that magic? No, that is science. All right, so we've talked a little bit about refraction. Now I want to teach you guys about reflection. Steve's going to help me get some of my materials out of the way here. Thanks, Steve. Another one for you. Now, glass has heaps of different uses. One thing that we can make out of glass are mirrors, right? You guys have all got mirrors in your house, probably in your bedroom. Make sure your hair looks really nice in the morning, probably in your bathroom too. Make sure you get your teeth really nice and clean. But how do we make mirrors? I would actually love for you guys to chuck into the chat there how you think we make mirrors. Do we combine lots of materials that absorb light? Or do we combine lots of materials that reflect light? So if you think you know the answer, put it in the chat. Let me know. Was it materials that absorb light or materials that reflect light? All right. Oh, I'm seeing some really good answers coming in. Polished metal. That's a fantastic guess. All right. We're getting a few answers in there. Lovely. I'm going to give you another 5, 4, 3, 2, 1. All right. Most of the answers in there are saying objects or materials which reflect light. And you guys are spot on. If we were using materials that absorb light, wouldn't be a very effective mirror, would it? No, not at all. We need to use materials that reflect light. And I've brought a few of those materials here with me today. So I've got this very cool paint here, and it's like a metallic silver color, very shiny, perfect for reflecting light. And I've also got with me here another beaker. Now I've taken that shiny metallic paint and I have sprayed it on the inside of the beaker there. And that has made the outside of the beaker really nice and reflective. If I take a look in there, I can kind of see my face, but it's a little bit distorted, right? That's because beakers are curved in shape. And the curvature of the beaker, that's actually going to, whilst it does reflect some of the light, it also refracts quite a lot of it, leaving me with a really distorted image. So not a very effective mirror. Let's see what else I've got. Right, I've also got with me here a really nice flat glass pane. So this one I think could work pretty well as a mirror. What I've done is I've sprayed this one with my metallic paint once more. And then if we look at the back of it, it should work pretty well as a mirror. So if I hold it up to my studio lights here, let that studio light reflect, I think you guys may even be able to see what I'm looking at. Can you see I've got a TV screen there? You may even be able to see my camera. That worked pretty well, but I think we can do better. So I've also got with me here another glass pane. Now this one is nice and clean, ready to be made into a mirror. I've also got with me some reflective tint. Now this reflective tint, it gets put on people's car windows so that you can't see through them. But I think it's going to work really well in making our mirror. Now, before I put that onto my glass pane, I need to give the glass pane a bit of a spray, make sure it's really nice and wet, ready to be made into a mirror. Then I'm going to get my reflective tint here, peel the plastic coating off, get that out of the way, put my reflective tint onto my glass pane. And then I've got this here, really, really super cool squeegee. I'm going to smooth all of the bubbles out, get it really nice and smooth, get rid of all of those bubbles. Now let's take a look at the back and see if that works. Oh my goodness, that is looking way, way better, right? Can you see me? Look, there's me on the big screen. Oh my gosh, I'm on TV. Wow, you can see my camera there. You may even be able to see Science Steve giving us a wave. Can you see him there? Hey, Steve. Awesome. So that's worked really, really well. You know why that's worked so well? Because glass is a super smooth surface. You can make mirrors out of other smooth things like plastic and acrylic, but glass definitely works the best because it's one of the smoothest surfaces we have. So that's exactly how they make all the mirrors in your bedrooms, your bathrooms, things like that. And if you've ever seen a mirror break, you'll notice it shatters into lots of shards, right? That's because it's made of glass. So just like glass shards. So if you ever see a broken mirror, steer clear because you may get cut and we don't want that to happen. So I had a lot of fun with you guys. I'm going to now pass it on back to Steve and we're going to see what other cool demos he has got up his sleeve.
How about a big round of applause for Taz? What a dead set legend. Give her a big clap. Well done. I'm going to clean up you. Taz, what have you done? There's oil, there's water. Let me wipe it down.
Messy, Steve.
Science can be messy, Taz. Now, you've done some pretty cool demos there, looking at refraction, talking about glass. Let me go even cooler, right? Let's crack out a little bit of liquid nitrogen, just for 5 minutes or so to have a little bit of fun. I've got a bowl. Now, the demos that I'm going to do with my liquid nitrogen for today, I'm going to use a special type of glass. Can you see this bowl? This is a Pyrex bowl. I can't just use any old glass bowl or container when I'm working with liquid nitrogen. Liquid nitrogen is the coldest substance that we work with here in our studios. Liquid nitrogen sits below. Does anyone know? How cold is liquid nitrogen? Feel free to throw it into the chat room. I'm going to grab my dewer. Yeah, let me grab it and stick it up there for you. This is full of nitrogen. How cold is it? I'll give you a moment. Tell you what, while you guys work that out, let me show you something really cool. I've written a note for you guys. Can you guys see my note? Let me get you nice and close here. I'll get my zoomed in camera for you. What does my little note say? Happy National Science Week. Science Week is the best time of year. I said that earlier. Now, this little note was written for you guys using a special type of marker. Have you guys seen these before? They're called thermochromic markers. Now, no one's got the temperature right yet. Oh, actually, there's one. I can't see who it is. Oh, the name's cut off. Minus 196 degrees. It's colder than that. That's the boiling point of liquid nitrogen. Colder than minus 196 degrees. So well done to you legends in there. Now, thermochromic markers were used to write this little note for you guys. Thermochromic, let's break down that word. Thermo, temperature, chromic, colour. These markers change colour depending on the temperature of the ink. Let me get you nice and close. I'm going to grab a lighter. Here we go. And I'm going to heat up my sheet of paper. Watch this. You ready? Little flame. I'm going to wave it around behind my sheet of paper. What's happening? You can see the flame there. Let me get that bit up the top. Try not to get my fingers because fire is hot. It looks like it's disappeared a little bit down the bottom there. There we go. Can you see the writing on there anymore? It's almost like it's disappeared, right? But it hasn't. All I did was I heated up my sheet of paper. The pigment inside the ink has gone colourless. That was a reversible change. So it looks cool, but I can reverse it and make that ink return. What's the opposite of heating something up? Cooling it down. Well done. So if I can cool down this sheet of paper, I can make that ink return. Do you believe me? Most kids do, which is great. Now, I asked Tasman to bring along a freezer today. I said, Taz, I want to do a really cool little trick with scientists all over the country who are tuning in today. And I said, if I heat this paper up, I'll give it to you and I'll stick it in the freezer. Taz, where's the freezer?
Steve, I forgot the freezer.
You've ruined national science.
I'm so sorry.
I know what. We don't need a freezer because we've got liquid nitrogen. I'm going to place this sheet of paper. It's got some typed up notes on one side and our message, which has gone blank on the other. Let me place it into this bowl. I'm going to grab a glove and put it on my hand. Let's pour some liquid nitrogen onto that sheet of paper and see if we can cool it down enough to bring our ink back. Let me take the lid off the top. Let's pour this super cold liquid into our Pyrex bowl. This Pyrex bowl can handle really cool temperatures. Here we go. Let's pour just a little bit on there. Just a little bit. There we go. Perfect. Now I need to grab that paper out. Not using that hand. Let me use this one. Let's make sure it gets nice and cold. Let me get you in nice and close again. I'm going to open it up and then blow on it. You ready? How cool is that? As soon as I cool down my sheet of paper, our message comes back and it says to you guys in my beautiful, neat scientist writing, Happy National Science Week. Oh, does that deserve a little round of applause? That was pretty cool. Now, while I've got my liquid nitrogen here, I can see it bubbling away in my bowl. Let me show it to you guys. I'll get you nice and close with my GoPro. Let me blow the cloud out of the way for you. Can you guys see? Not really. Let's get some more in there. Let's have a look and see the liquid nitrogen bubbling away. Let's get a bit in there. It makes a big cloud. We'll wait for the cloud to move on. Can you guys see? You can just see it. There's a liquid like bubbling away furiously. That is the liquid nitrogen. The liquid nitrogen looks a lot like water. And as soon as it goes into my bowl, it starts warming up. It starts grabbing heat from the environment. As soon as it gets warmer than minus 196, it starts turning into a gas. Can you see this beautiful cloud around me? That is not nitrogen gas. Nitrogen gas is colourless. It's invisible. You can't see it. In fact, most of the air around us is made of nitrogen. So this cloud is made from little droplets of water that were in the air that have floated on down. They've cooled down, they've condensed into droplets, and then they've been pushed away by the nitrogen gas. If I blow into my nitrogen, my breath is loaded up with water. Let's see what it does. There we go. Makes a beautiful big cloud because, again, that water vapor condensing so that we can see it. Now, in a moment, Taz is going to come back in and she's going to talk to you guys about glass, and she's going to show you what happens when we heat it up and then cool it down. She's going to have a normal glass bottle, not this special Pyrex glass. So, while I've got some nitrogen, let's just have a look at an everyday material like this beautiful rubber ball. I'm going to stick it in some liquid nitrogen and make it really cold. What do you reckon is going to happen to my ball? Feel free to stick your answers in the chat room because I can see them. My ball at the moment, if I'm observing its properties, it is orange in colour. It's quite elastic. It bounces beautifully off my lab bench. Taz and I will be able to play handball with it, hopefully a little bit later on this afternoon. Really cool to see some of the answers going in. Some people said my bouncy ball is going to shrink, it's going to lose its colour, it's going to become brittle, it won't be able to bounce anymore, it's going to explode. Now, the only way to find out what's going to happen is by, I suppose, dropping it in. So, here it goes. Gloved hand. Let's drop it in to the liquid nitrogen. I don't need to leave it in there for very long at all, but I do need to grab something to pull it out with. Aha. Now, if you listen closely, you can probably hear the nitrogen bubbling. You might even be able to hear the ball as I knock it around. Can you hear that? Someone said just now, I've seen this before. It's going to rip into pieces. Oh man, I hope so. Let's get it out. The ball's been in there for how long? 30 seconds. It started to lose all of its heat energy. So if I grab the ball out now, ooh, it's very cold. Let me tap it against the glass. It's gone. Oh, rock hard. Now it hasn't frozen because it wasn't a liquid. When we talk about something freezing, that means it goes from its liquid state into a solid state because we've removed heat energy. Yes, we've removed heat, but we didn't freeze it. We've just made it really cold. When it got really cold, those rubber particles, they were able to flex and stretch and bounce. They've cooled down and they've lost their heat energy. So they're not able to move as well as they used to. So now it's gone really hard. It hasn't exploded. It hasn't shattered. Doesn't matter how hard I throw it at the table. It just turned into a big hard ball that is not flexible at all. But it's okay. If I go and add some heat energy to it from my body, if I blow on it and rub it in my hands, I can give it back some energy and those particles start to get flexible again, which means if I warm it up enough, Taz and I are still going to be able to play handball at the end of the day, which is the most important thing, I reckon. Still not bouncy, but we'll give it a little bit longer. All right. Now, Taz wants to come back in a moment. Before you do, Taz, let me do one more demo. I want to make something explode for all these young scientists. Let's get our liquid nitrogen and let's put it into another container. Let's grab this glass sidearm flask. Have you guys seen these before? This again is made of a special type of glass, especially for my science lab. This glass can get really hot and really cold. It's called borosilicate glass. So if I take the lid off, I can pour or decant some liquid nitrogen down into that bottle. As it goes in, it starts to warm up and bubble away. If I stick a lid on, as that nitrogen boils, I can force this cloud out the side. When nitrogen boils, it expands over 600 times in volume. Let me grab another glove. I'm going to put a balloon on that little side arm and I'm going to stick the lid on the top because I want you guys to see how much space that nitrogen takes up. I couldn't do this in a plastic container. The plastic would get too brittle and it would crack. I couldn't do it in a rubber container because again, it would expand and it would burst just like my balloon does. But I can do it with glass. Now, this balloon's going to get big. Anyone in the studio, be warned. Feel free to cup your hands over your ears. I'm going to stick the lid on. Here we go. Let me hold the balloon on. Oh dear, it's getting big. We normally get 5 or 6 little bumps before it goes. Can somebody cover my ears? Oh dear. 1, 2, 3, 4, 5. Get ready. If it goes bang, how about a big clap? Ready, steady. It's going to be loud. Oh, golly gosh. Did you hear that? Oh, I'm going to get out of here and let Taz step back into the studio because I've taken up enough time. Before I go, let me flip my bottle upside down and get rid of the last of that liquid nitrogen to make a nice big cloud for Taz. Tasman, over to you.
Oh my goodness, Steve, I think I've gone deaf. That was the loudest bang I've ever heard. Huge. All right, so Steve told us a little bit about how some glass can be specially designed to withstand extreme temperatures. So Pyrex glass, like maybe your parents or your grandparents have used in the kitchen, like that bowl that Steve was using, it can handle really hot temperatures and also really, really cold temperatures. But not all glass can handle that. So I've got with me here a glass bottle that had some ginger beer in it. Now, this glass bottle was not designed to withstand thermal shock, so getting super hot or super cold. So I think I would like to try a cool experiment. I'm going to try and heat this glass bottle up and then immediately cool it down, and we're going to see what happens. So exciting. So to do that, I'm going to need a nice cold ice bath. So we've pre-chilled some water here. Let's get that in there. We're going to get all the nice big ice chunks. And I think we're going to need to cool it down just a little bit more. To do that, we're going to need some more liquid nitrogen. Steve is ready to go. Let's get it really nice and cold. Beautiful. That looks cold enough to me. But we now need to get this glass bottle really, really hot. So to do that, I'm going to set it on fire. How does that sound? First, let's give my ice bath a nice little stir. Make sure it doesn't freeze over. That wouldn't be very useful, would it? No. Give it a stir, get it nice and cold. A bit like a witch's cauldron. Looks amazing. Okay, so now I need to get my glass bottle really, really hot. So like I said, I'm going to set it on fire. Sounds pretty fun, hey? Now to set it on fire, I'm going to need to use some flammable liquid to do that. So I've brought a flammable liquid with me. Here it is. Now this flammable liquid, we're going to need quite a lot of it. And you may notice that it's green in color. That's because it's not just a flammable liquid. We've actually put another material in there as well. We've put some copper. Now, the copper will not only change the color of the flammable liquid, but it's also going to change the color of our flame. Doesn't that sound fun? So we're going to make sure it's really, really nice and doused. What I'm doing is I'm putting the flammable liquid all over this twine here so that we're only going to be heating the glass bottle in a specific spot. All right, so get the rest of that on there. It's looking really nice and doused now. Steve's going to clean up a little bit for us. We've got to be safe when we do science. Beautiful. So now I'm going to light that twine on fire. There we go. Get it going. Are we ready? Wow. Can you guys see that green flame? Isn't that incredible? Wow. All right. We're really going to let it get nice and hot. And I would like you guys to put your answers in the chat now of what you think is going to happen when I put it into the ice cold bath. Let's make some predictions. I want to see what you guys think is going to happen. Oh, it will explode. Oh my goodness. Thank goodness I'm wearing safety glasses then. We're going to get a big flame. Someone thinks it'll go green. You think the whole bottle will go green? That's a pretty interesting prediction. All right, it's getting really nice and hot now. Someone thinks it's going to shatter, break. Okay, we're getting lots of very similar predictions there. You guys seem pretty switched on. And we need to make sure it burns for quite a while for this experiment to work. I think that flame's nearly gone out. I think we might nearly be ready. What do you reckon, Steve? Is that long enough? All right, let's see what happens in 3, 2, 1. Oh my goodness, look at that. All right, so it didn't quite shatter, but it broke clean in two. So clearly these glass bottles cannot handle thermal shock. That was pretty cool. What do you reckon, Steve? Was that pretty fun?
I think that deserves a round of applause, Taz.
Woo!
Well done. Now, we are nearly out of time, Taz, so please don't run out of the studio.
No,
Let me grab
safely dispose of this, don't I?
a broken glass bucket for you.
Beautiful.
I reckon we finished with one final demonstration for these young scientists. Now, it is National Science Week, so I want to finish with something pretty epic. We said earlier on that glass can be coloured. We've got some brown or amber glass. I've got some green glass down the end and some clear glass, which is our natural colour when we just heat up sand and then cool it. To create coloured glass, we simply add some additional compounds to our sand and we heat them up. We get some oxides that we dig up out of the ground. We can do the same thing to fire. So we can add additional ingredients to our flammable liquids to make coloured fire. So Taz, I thought, to finish our presentation today, let me get our glass out of the way. Let me set up a Bunsen burner in the middle. And I thought you and I could spray some flammable, colourful liquids across the fire and see if we can end up with coloured fire. What do you reckon?
That sounds like a super fun idea. Let's do it.
Okay, I've got my gloves on, I've got my glasses. How are you looking?
I'm looking safe.
Brilliant. Let me light our Bunsen burner, first of all. I'm going to make it a safety flame so we can see it. What colour is that burning, Taz?
It's looking a beautiful orange colour to me.
Excellent. Now I'm going to squirt some methanol into that fire. Methanol is pure alcohol. Right? I'm going to squirt it in. What colour is that fireball?
It's like an orangey blue, isn't
Yeah, it's
it?
got blue in there. It's a pretty hot flame,
Yeah.
but it's generally orangey colour. Now, I've got the same chemical here, but I've added some strontium. So let me squirt it in. In the chat room, let me know what colour this one goes. You can see it on Taz and on colour. There's a beautiful red colour. Oh, look at the chat room. It is going off.
That's
All
so
right,
clever.
Taz. I've got some strontium in mine to make it go red. Tell me what you've got.
Let's see. I've got some copper. Let's see what colour it turns that flame. Whoa.
Oh, Taz, that looks incredible.
That's
We had
amazing.
greens and blues because we had copper. Now, to finish off, I want to make a multi-coloured fireball. Now, I know you've been juggling fire all over the place during your National Science Week shows, but we're in the studio today, so we're not going to get it too high. But for all of those scientists out there who are celebrating National Science Week with us all over the country, let's get a countdown from you guys, right? A coloured fireball. 5, 4, 3, 2, 1. Let's go, Taz. Multi-colour fire. There we go. Woo! Oh. How about a round of applause for that? Hey, Taz, I've had so much fun. Have you guys had fun today? Doing some extra science, celebrating National Science Week. Hopefully you've learned a little bit about glass. Taz was obviously very educational when she talked about refractive indexes and she broke her glass. Hopefully I just came along and had a bit of fun with you. Now, we've got to get out of here, Taz, because we've got a very busy afternoon. Scientists like us don't get to sleep. I know Karen wants to jump back in and say g'day. If you're in New South Wales, DJ, another scientist, and I are coming down to Sydney. We're going to Parramatta for a big family science day on Saturday. So check it out if you want to see us in person. The guys from physics are going to be there as well, getting crazy with their science shows. So is the surfing scientist, who is one of my really close mates. get amongst it. We're out in Parramatta on Saturday. Karen, we've got to get out of here. Everyone who's tuned in today to SciFest 2022, happy National Science Week. We'll see you guys next time.
Excellent. Thank you so much to both of you. That was so much fun. We had so many questions and comments coming through. Absolutely fabulous. Once again, everyone, thank you for joining us for SciFest, celebrating everything science and celebrating National Science Week. A big thanks to Inspiring Australia New South Wales for letting us put on these sessions. And yeah, what a great way to kick off day 4 of SciFest. So thanks, everyone, and hopefully we'll see you again soon. Bye, guys. And don't forget, if you're near Sydney, go to Parramatta, see the Street Science team in person.